Right. Thank you. Can everyone hear me? Hear me well? All right. Great. Okay. So I'm Alexander Bessman. I have been the maintainer of the Pocket Science Lab Python library, among other things, for the past 5 or so years. And during that time, I have learned some things about testing hardware adjacent software that I would like to share with you today. So I'm going to go over these points. Why is it difficult? How can it be done using PSA Python as an example? Spoilers alert for that is that the way that we used to do it in PSA Python is no longer how we do it today, and I will explain why. I'm going to go on a bit of a detour, explaining or investigating, discussing why should we even unit test hardware drivers in the first place? What is the benefit? After trying to answer that question, I'll get back to the how, and finally some key lessons. So first of all, why is it hard to unit test hardware drivers? And just note on terminology. When I say testing throughout this talk, I mean unit testing unless I specify otherwise. The reason it's hard to test hardware drivers is state. Hardware is stateful, and state is difficult to model. Like ideally, when you are writing software tests, you want this situation. You want to have like a function or a class or something like that that takes some input, does something with it, and spits it back out in a neat deterministic way. So you can just check in your test: is the output what I expected? If it is, good, the test passed. If it isn't, bad, the test failed. But in reality, when we're dealing with stateful systems like hardware, we have this situation. You put something into the function talks to the hardware has state, sends something back, which we don't know because it's difficult to model state. It's technically deterministic, unless it's like some kind of quantum random generator, but it's very difficult. In practice, you can't know what state the hardware is in. That means we don't know what our expected output is from this function. So we can't test it in this manner. How can we deal with that? Well, the most obvious way is to just keep the hardware in the loop. But if we do that, the tests become sensitive to the order in which you run them, because the tests themselves, when you run them, affect the state of the hardware. The tests become sensitive to hardware fault. If something breaks, your tests will fail, and it's not going to be immediately obvious why they're failing. And a significant problem for open source projects specifically, like the Pocket Science Lab, is if your tests depend on having access to the hardware, you are basically eliminating the possibility for new contributors to contribute to your software because they don't have the hardware. And this type of testing, where the hardware is present in the testing loop, is not unit testing. It's integration testing, which is also good. That's something you need to have. But you ideally also want unit tests. Perhaps I should mention that what unit test is, if someone is not familiar with that. The idea with unit testing is that you subdivide your software into small, individually testable units. Yeah, and I'll get back to how you do that in a bit. So as an example, this is the current sort of software stack or architecture of the Pocket Science Lab. Over here is the user. The user interfaces with the, in this case, PSA Python via one of these instrument drivers, which in turn talks to the UART driver, which talks to the hardware. So when the user puts something into, let's say, the oscilloscope, okay, I want to get some samples from the oscilloscope. This module calls the UART driver, which sends some bytes over to the hardware, which does something, sends some bytes back, which are handled by the UART driver, which then return those to the oscilloscope module, which does some post-processing and hands the output back to the user. This is the case for every instrument. And that means that each of these modules is stateful, because each of them calls the hardware, albeit indirectly. And that makes all of these very difficult to test, because each of them is stateful. So one of the first things I did when I started contributing to PESA Python about 5 years ago was I added a test suite, like a way to eliminate the hardware from this test loop by recording the bytes sent by the UART driver to the hardware while we were running integration tests. And then when we wanted to do unit tests, that is without the hardware present, we just replayed the exact same bytes that we got during integration tests. So this eliminates, theoretically, the need to have the hardware present to run the tests. This worked well for some situations. Like one thing that it is extremely reliable. So if these tests pass based on the recorded traffic, you can be very, very certain that nothing has broken. Like if you send the same bytes to the hardware will respond in the same way. So this is, in that sense, it's actually a very good test, because you know that if the test passes, you can be certain that your driver is still functioning as intentional. It's also low complexity. Like mocking interfaces is a notoriously difficult problem, but just recording and replaying traffic is really very simple. Yeah, there's no real need to like model internal hardware states. You just record and replay. So in that sense, it's both reliable and simple, but it has some drawbacks, some quite significant ones, it turns out. This added very significant maintenance overhead, this approach. Basically, the tests became too specific. Very, very minor changes in the code resulted in a need to re-record not just like one test, but in many cases, lots of tests. Because something like if you change something in the UART driver, every single test just started failing. And yeah, then that's something that a maintainer, meaning me, had to go in and re-record, re-upload the recorded test data for basically every little change. So that was pretty annoying. And in practice, it turns out it didn't really eliminate the requirement to have access to the hardware, because again, if every change breaks the tests, then you can't actually make use of the tests again unless you have the hardware. As a case in point, this is a pull request against PESA Python. It's super simple. This pull request fixes a problem. It's not really a problem at all. This already worked fine in Python, but basically there was a difference between the Python and the Java implementation of the triangular waveform function, because Java and Python handles the modulus operation differently. The details aren't important. The point is that this is a super small, trivial change. And it resulted in this really long, well, it's not really long, but it's like kind of significant discussion on like back and forth. This isn't working. Why isn't it working? The tests aren't passing. Okay, yeah, basically lots and lots of maintenance overhead for like trivial changes. So we ended up abandoning this approach. We no longer use this recording, replaying-based unit testing. We still use the integration tests, but not the unit tests. It worked well, but added too much maintenance burdens. So at this point, we're going to take a step back and ask ourselves, what is even the point? Why do we want to test the hardware driver? Like what is our goal? What is our end goal with that? So is it this? Is it that? I mean, honestly, I'm gonna be honest with you. This is definitely something that I want. It looks nice. It looks really nice on the GitHub page, but it's not a really good reason to test. Like that shouldn't be the core reason. Company policy says so. I mean, if you work for a company, your boss tells you you got to have unit tests. You're gonna write unit tests. But why does the company policy say so, though? Do we test software to make sure it works? Is that why? Yes, yes, in the sense that, the chicken crossed the road to get to the other side. Yeah, okay, we test software to make sure it works, but like that's not like a good answer to the question. It's true, but it's not a good answer to the question. It doesn't really explain anything. So, attempting to answer the question, every software exists on a scale of like severity of worst case scenario. If the software stops working, if the software breaks, what is the worst thing that can happen? On one end of the scale, like the user is like kind of annoyed, right? The software isn't really doing anything very critical, but it broke and the user is annoyed. Okay, on the other end of the scale, the user dies. Uh-oh. Depending on where your software is in this scale, the answer to the question why test software will be very different. On this end of the scale, the point of testing, I would say, is that it saves you as a developer time. Like you can sort of stop thinking about whether every little change breaks your software, and that relieves you. It lessens your cognitive overhead unless you focus on writing better software. Whereas on the other end of the scale, the point of testing is to not kill the user, right? This means that if you're on this end of the scale, you have to accept that testing, like you must test, even if testing turns out to be very difficult, even if testing adds very significant overhead to your maintenance burden, you still have to test. But most software, at least, let's say, open source software, the kind of thing that we're dealing with here, probably leans towards like this end of the scale. And that means that you actually have the luxury of deciding sometimes maybe it's not worth testing every single thing. And this is true for all software on both ends of the scale. Testing your software encourages developers, that means you, to write testable software. And this is extremely important. This, I will argue, is the single most important property of software testing, making you, the developer, think about your interfaces. Is the software I'm writing testable or not? That, unfortunately, or maybe it's fortunate, I don't know, is very difficult to like quantize. Test coverage is easy to quantize, and anything that is easily quantizable falls into Goddard's law, which is when a measure becomes a target, it's easy to be a good measure. So again, that 100% coverage is like, it looks very nice, but it's not a good target for, like, it doesn't actually tell you much, if anything, about whether your tests are good. So this is kind of okay, tongue-in-cheek here, but when you're first starting out as a software developer, you don't have a whole bunch of tests. You're just writing software because it's fun and it kind of works. And if the build passes, you're like, good, I'm happy. And then as you grow as a developer, you add, your GitHub page starts looking like this. You add tests and linters and all manner of things, and eventually you sort of tip over and realize, maybe I don't need all of this. I'm not saying that you necessarily go back to this, but like there is a cost. There is a cost to doing all of this, and if it's not paying, if that cost isn't paying you back in terms of like writing better software, you should stop doing it. Anyway, getting back to the how of how to test hardware drivers, or really any stateful stateful software. The problem with the PSI Python architecture is that the entire thing is stateful. And the way to fix it, so this is something that is like a work in progress. We're not quite here yet, but the way to fix it is to move the statefulness closer to the hardware. You can't really remove the statefulness entirely because it is a hardware driver. It has to keep track of what the hardware is doing. Somewhere in the driver, there's going to be some kind of model of the hardware, and that is stateful. But you can refactor a lot of it to not have state, to be stateless, deterministic. Like instead of the user calling the oscilloscope, that propagating all the way down to the hardware and all the way back up, you can use a dispatch model with the loose coupling, which uses like individual functions like this to pre-process the user input, turn that into something that you can send to the hardware via the UART driver. And once the hardware responds, you don't propagate that back up to the same function. Instead, you call like something else. And in this case, all of these just have a very simple input-output deterministic stateless, easily testable. But what about this part? We still have state. How do we test this? Now I'm going to say something potentially controversial. Maybe don't. Like I said, when we're writing software that is not safety critical, that is not going to kill the user, we have the luxury of actually thinking about, does a test help us, the developer, write better software? Like we could test this. It's perfectly possible to like mock this. You could use either the record replay that we used previously or some other form of mocking. But mocking is inherently complex. It adds a lot of complexity. It adds maintenance burden on you, the developer, that could be better spent elsewhere. And that is a difficult balance to find. But one of my sort of key lessons in this is that sometimes it's okay to not test hard to test parts of your code, because you can spend that effort elsewhere and make the software better. If you do that, though, you have to make sure to keep this part small and simple. Like the implementation can be simple even if it's difficult to test, simply because it has state, like I said. But if the implementation is simple, then it still doesn't add that much cognitive load on you, the maintainer, to think about, okay, when a change is made to this part of the code where you don't have a test, the code is simple enough that you can still just reason about it in your head without too much of a cognitive overhead, and still be like confident that the change doesn't break everything. So key takeaways, lessons learned from this. How do we test hardware drivers or any stateful software? There's no shortcut to this. You do it by writing testable software. Like if you're inheriting a legacy code base which doesn't have tests, and you're thinking to yourself, okay, I want to add tests to this. Don't. Maybe add some tests, but don't like go all out. Don't try to test something which is not neatly subdividable into units. You cannot unit test software which doesn't divide into units. You just can't do it. What you should do is, maybe write a few. They're not really unit tests at that point, but more like integration tests to make sure that you don't break anything too badly into something that is unit testable. That is how you test hardware drivers. And the reason why you want to do that is because you want to write testable software, because testable software is maintainable software. The single most important property of tests, in my opinion, is not to show you in like automated testing, okay, something broke. That's important. It is important for tests to do that. You're making a change or you're reviewing a pull request or something. The tests tell you, okay, did this break something or not? That's super important. But this is more important. This is the most important property of testing. They make you think about your architecture. Is it testable? That's why you should have tests. Okay, final points. Stateful software is hard to test. Testable software is maintainable software. Tacked on tests, which is sort of what we did in PSLab Python. They may be worse than none at all because they make you, it slows down development. If you have to stop and fix all of your tests for every little change, those tests aren't worth it, and you should not do them. Tests should decrease maintenance load. Otherwise, don't bother. The exception to this is if you're on the very, very right end of the scale that we saw earlier, right? If your software can kill someone, the maintenance load doesn't really matter. You gotta test anyway. But usually that's not the case. And 100% test coverage is often not worth it. And in fact, I would almost consider it code smell. It's not really code smell, but you get the point. I'm very, very skeptical these days of software which claims to have 100% test coverage. That's probably something fishy going on, in my opinion. All right, so that's what I had. If you're interested in the PSLab, they're available for sale from the front desk. I think they're 1,500 baht. If you want to play around with them yourself. Tomorrow, we also have a series of workshops on the PSLab if you want to test them out, get some hands-on experience with them. Yeah, so I think we have time for some questions if you have any.
Anyone has any questions? We'll pass you the mic. Okay.
No.
So
yes.
So like, is it also like some like, do we also have tests for the firmware? Like, or is it possible that we also move some product tests to the firmware so that it can dynamically respond if something on the layer has been?
That's a really great question. So currently in the PSLab, we don't have tests for the firmware. The reason for that is that the firmware doesn't build for any target except the actual microcontroller. So we can't like build it with GCC at the moment. So the only way we could test the firmware is using like a simulator, and that first of all is not a unit test; it's some kind of integration test. And the simulator is like proprietary, so no, it's not worth it. But we should. Like one thing that I would like to do with the firmware is to make it so that, yeah, it's more modular, so that you can compile individual modules using GCC and then test those modules. That is something that could be done, and that's something that we should work towards. Yeah. Okay.